Okay, we're going to look at applications of Newton's laws. And basically, we are going to just continue what we did in chapter 5 and apply it to more complex situations such as connected bodies. So again, the assumptions hold already. Objects behave as particles. We're going to ignore rotational motion, which is something we do at the end of the course. Masses of strings, ropes, cables, etc. They're all 0. So we'll be interested in only the masses of the objects. And we're only interested in forces acting on the object. We can neglect reaction forces. So for instance, if a box is sitting on the table, we're interested in the table's normal force onto the box. We don't care about the box pushing down on the table if the box is what's of interest. So a lot of this is going to be drawing free body diagrams, analyzing individual objects, and applying only those forces that act on those objects. All right, connected body problems. When we have multiple objects, we want to connect the forces between one object and the other. And oftentimes they're connected by a cable, which forces them to move with one another. So we'll see there'll be a connection between forces, usually tension in a rope, and acceleration. So connected objects, again, typically there's some type of rope, cable, or whatever joining the two, or at least making the motion the same. So oftentimes acceleration in magnitude is the same, and the tension in magnitude is the same. So in the case where we have two objects, mass 1 and mass 2, and they're both connected, we'll do an equation for mass 1. We'll do an equation for mass 2. It's going to be a little bit different from what we did with Newton's second law. We said the sum of the forces is equal to the mass times the acceleration. But sometimes the acceleration of one object is equal and opposite to the acceleration of the other object. So sometimes you'll see us write, instead of just the sum of the forces is equal to mass times acceleration, we'll either put a positive sign there, or sometimes we'll put a negative sign there. So don't be distracted by suddenly introducing a negative sign within Newton's second law. What that is doing is saying that if I call A's acceleration to be positive, and B is moving in the opposite direction of A, or moving in a negative direction, I need to be able to put that negative in there so that this acceleration makes sense in terms of the other acceleration and the coordinate system that I've chosen. Remember, the negative and positive sign just denote a particular direction, okay? And mass 1 can be accelerating in the positive x direction, while mass 2 could be accelerating in the negative y direction, okay? Just allows us to connect the two bodies together. Okay. So apply Newton's second law separately to each object. The magnitude of the acceleration will be the same. The tension, or the magnitude of the tension, will be the same. But of course, we might have that negative and positive sign. All right. The easiest system to look at is Atwood's machine. Atwood's machine was used in 1784 by George Atwood to measure the acceleration of gravity. Even though Galileo had shown that the acceleration of gravity near the Earth's surface was constant, he wasn't able to measure it because later on we will see that when you have a rolling object, it has rotational inertia, which means that it not only resists movement due to its own mass, it resists rotation. So the balls rolling down his inclined plane would actually give an acceleration that's too slow given the angle, because some of the energy and some of the force was going in to actually make it roll. So generally, when we have this, we have two masses connected to a frictionless pulley. We neglect the mass of the string of the pulley. We make one mass slightly less in magnitude than the other mass. So here very clearly, mass 2 is heavier, it's going to go down. mass 1 is lighter, it's going to go up. Here's what I was talking about. Look at the direction of the acceleration. If I were to connect the two accelerations of each, I would say M2 has a negative acceleration in the y direction, while M1 moving up has a positive acceleration, okay? Think about this. M1's lighter, it's going to go up. M2's heavier, it's going to go down. And that's why, sometimes we'll write that F equals ma as the sum of the forces in the F direction is equal to negative ma. All right. So again, what mass 1 is doing, mass 2 is doing the opposite. As mass 1 goes up, mass 2 goes down. Okay, let's identify forces first of all. Disconnect the objects from their system and draw free body diagrams. Here is M1, okay? We have tension pulling up, so that's going to be a positive force. We have weight pulling down, that's going to be a negative force. And each force, tension plus weight, are going to add up to be equal to the mass times acceleration. That's Newton's second law. Okay? Same thing for mass 2. Mass 2 is the same tension as mass 1. So I won't call them the tension T1 or T2. I'll just call it T. Okay? And there's the weight. Again, tension's up, weight is down. All right, so I did my free body diagram. I know where my forces are, this, 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 this. I'll come up with two equations, and I'm going to solve them simultaneously. I'm going to have an equation for the sum of the forces on the first object, and I'll have an equation for the sum of the forces on the second object. In both cases, it's going to equal mass times acceleration. All right. Again, mass 1's going up, so its acceleration is going to be upward. Mass 2 is going down, so its acceleration is going to be downward. And I've got to be careful about that when I incorporate that into the equation. So mass 1, sum of the forces, F equals ma. F equals ma. Tension up, weight down, M1A, that's equal to the sum of forces. Now, I don't know two things here. I'm missing two pieces of information. All right. I don't know the tension, and I don't know the acceleration. Those are the two quantities I don't know. I'm going to be given M1, I'm going to be given M2. All the other forces are negligible. I need to get a relationship between tension and acceleration. So again, I assume that I know M1. So I set my equation in terms of tension, and although I would have two unknowns here, I don't know tension, I don't know acceleration, I can relate the two quantities to one another. One equation, two unknowns. All right, do the same for mass number 2. And again, be careful here that you get your sign correctly. Okay, mass 2. Mass 2 is going in the negative direction. That acceleration is negative. So I write this equation, notice what I've done. Negative M2A. All right, the sum of the forces equals mass times acceleration, but because I'm relating this acceleration to the previous acceleration, I've got to give it a sign. Okay. Once again, I get an equation that relates tension to acceleration. And think about algebra. Back in algebra, you had two equations, two unknowns. You could solve for the unknowns. It's what we do a lot of in this course, especially for these connected body problems. We get multiple equations and we solve for the, we did it for statics, for the multiple systems. Okay. So it's like a jumble here. I've got my first equation. There's my mass 1 equation. I know it's from mass 1 because it's got mass 1 in it. Here's my mass 2 equation. And one of the simplest means to solve when you have this case is take one of the unknowns, in this case, I don't know tension, and replace it with that expression right there, right? Tension equals M1G plus M1A. So I place that where tension used to be, and now I can solve for my unknown, which is A, okay? All I've left here as an unknown, everything else would be given, right? I know M2, I know G, I know M1, I know G, M1, M2, A and A, those are the two things that are unknown. All right, the rest is algebra. We're trying to figure things out. Get all your accelerations to one side, get all your non-accelerations to the other side. So I move this A over here by adding it to both sides, okay? I'm left with one side with just G, one side with A, okay? I simplify terms. I just combine the two terms that are G and the two terms that are A with the parentheses. I now solve for A by dividing both sides by M1 plus M2. And I get my final equation. Acceleration equals G times M2 minus M1 over M2 plus M1. Let's think about this equation for a second. I know this thing's going to go faster the bigger the difference between M2 and M1. That's taken up by this numerator right here. The heavier M2 is compared to M1, the faster the whole system's going to go. It's going to be more unbalanced. So that difference represents that degree of unbalance. Also, the heavier the combined mass of the two, the more inertia it has. M1 plus M2 is the total inertia of the system, the slower it's going to go. The best I can hope for acceleration is, since this is powered by gravity, the best acceleration that you can have is basically 9.8. Can't go any higher than that, right? 9.8. All right? Think about this. If I were to take M1 and just cut M1 off, M2 would fall at the acceleration of gravity. If I were to make M1 go to 0, it would effectively be like cutting the string. M2 would accelerate at 9.8. So I can never do anything faster than 9.8. If you ever do an Atkinsons machine, or generally a problem where you have the acceleration of gravity powering the whole thing, and you get an acceleration faster than 9.8, you did something wrong. Here's one place that a lot of people make a mistake. Sometimes they'll mix up the signs. Okay, maybe they'll have a plus sign up here, or they'll make this negative down here. Just when they're doing the algebra, something goes wrong. In that particular case, you get an answer greater than 9.8, you can go back and check to make sure each step has the right sign. Again, never can go faster than 9.8. And in fact, that was one of the questions in experiment 3. So again, you can see here, a big difference in mass, big acceleration. A moderate difference in mass, less acceleration. Very little difference in mass, very low acceleration. In fact, if they're balanced, the thing's not going to accelerate. Okay? Don't memorize this equation, by the way. Know how to derive it, because on a test, I'd ask you to derive that. Okay.